In this video, we're going to talk about batch export and analysis in RCB. So we're going to talk about why we need to export files from RCB to the SLB and PTD programs. We'll find out exactly what the batch export tool is doing, and we'll have a look at some of the settings in depth, so the reaction settings and the long-term deflections. This video will focus on the SLB software, batch export to the SLB. Batch exporting to PTD and generation of auto tendons will be covered in a separate video. Looking at an overview of the INDUCTA software, we'll see why we have to export files to SLB and PTD. So the RCB model is the central 3D model where we input our loading including lateral loads. We then perform the global 3D analysis. We can design columns and walls in RCB. However, to design individual floors, we have to send them to SLB for a reinforced concrete design and PTD for a post-tension slab design. Why we do this? So for a few reasons. The RCB software only uses Igross. So all of our deflection calculations will be off by a factor of about 2 to 3 in RCB, our long-term deflections. SLB uses iCracked and designs the reinforcement. So to get accurate long-term deflection results, we have to send it to SLB and to PTD. And RCB cannot model tendons, so if we want to do a post-tension design, we have to send it to the PTD software. So as we'll see in the coming videos, we can export multiple floors in bulk, have the SLB and or PTD programs launched silently in the background, and then we can view their results in RCB without having to leave the RCB program at all during the preliminary design stage. So we'll go to RCB now and have a look at exactly why we need to run the batch export in more detail. So it's the model that we've been working on in the previous few videos, just this medium-rise residential building with basically some typical upper floors and a transfer floor. And the analysis has been run. We have some results, loadings input, all of that's done. So in the RCB software, we can view Igross deflections, so uncracked Igross values. So if we just show this for one of the typical floors, let's say maybe level 3, let's say 4. So for a service load case, we can see we have some values displayed on screen here. Now, because this is Igross uncracked, and if this is going to be reinforced concrete, the general rule of thumb is that the long-term cracked section deflections will be greater by a factor of 2 to 3. So one of the reasons why we batch export to SLB is so that we don't have to make that approximation. We can get accurate values calculated for us directly by the SLB software. The other reason why we export to the SLB software is to get rid of the effects of basically secondary effects of shortening of the lower floors. So if we zoom in, we see we have some displacement at the middle of the span, but we also have displacements on the walls as well. So what this is probably what's happening is we have some deflections occurring on the transfer floor. So the transfer floor is deflecting, and then those deflections are basically they're carrying up to the walls on these upper floors as well. So we may not want to be seeing that when we design our slab. Currently the model has been essentially it's essentially come into existence in one go. However, with construction stages, with construction leveling, this particular floor will be constructed flat. It won't be constructed on the displaced shape of the level 1 slab. So we may want to get rid. We might not want to see the secondary effects of the deflections of the lower floors when we design slabs on the upper floors. So that's one reason why we export individually to the SLB and PTD programs. And the other reason being we don't want to have to guesstimate deflections in RCB. So, and this is just for Igross. Now, I'll show you one more tool that we have in RCB related to deflections, and this is under Reports and Maximum Slab Deflections. So what this is, it shows us the maximum relative displacement of the slab on that particular floor. So what we see, this is, I believe it's for the maximum, or 1.2G 1.5Q case. And the purpose of this report is to indicate to us, have we forgotten to put a column in, have we forgotten to put a wall in. So all I'm looking at, basically, do I see any values here in meters? So do I have 1 meter deflection? Did I forget to model a column? Should I go back and just fix up that area? In this case, it looks okay. There's nothing missing. And what I mean by relative displacement is that we get the deflections at the walls and we take that out. So basically what we're looking at here is displacement of the slab. So if we were to go up to the level 14 roof, for example, we would actually see absolute values bigger than this, this 19 mil. Yes, so just showing the absolute values of the deflections on that particular floor, worst case. Not to be used for design, but is just indicative and tells us whether or not we have forgotten to model a vertical element. So again, this is all done via Igross. To have accurate long-term crack section deflections, we need to run a batch export and analysis. So that is done under Solve, SLB PTD batch. So what happens here, just in principle, is that for the selected floors, so for example like so, if we were to do it like this, what would happen is that RCB would export based on our predefined settings, levels basement 2 and basement 1 to the SLB and PTD programs. These programs will then launch silently in the background. Basement 2 and basement 1 will be run, and then we can view the SLB and PTD calculated results in the RCB software. So the thinking is that during the prelim stage, we don't have to leave the RCB program. During the preliminary stage, when we're determining slab thicknesses, as governed by long-term deflections, we don't have to leave RCB. Now, we'll talk about these various settings in more detail, so the reaction settings and the long-term deflection settings. This export directory setting is pretty straightforward. This is where the individual files for SLB and PTD, as they will be created, where they will be sent. Okay, so we'll go back to PowerPoint and have a look at a few more slides. So here we have the export and analysis settings, which can be done just as individual, basically individually per level, or the same settings for all levels. So we have a few options here about the how we are going to export the reactions. We also have an option to export moment field. Now, export moment field won't be discussed in this video. It will be discussed in more detail in coming videos. And then we have long-term deflection settings, which we'll discuss. PTD preliminary settings will not be discussed in this video, so automatic tendons, things like that, that will all be covered in a separate video. So firstly, we'll look at the reaction settings. And to understand what batch export is doing, to be able to use the batch export and analysis correctly, we have to have an understanding of what's going on with the reactions. So basically, we're not going to see any of this when we perform a batch export and analysis, because basically it's just exported. The SLB file, for example, is run by itself in the background. But these screenshots, these following set of screenshots, will show what is being exported to SLB in terms of reactions based on the various settings. So we understand what we're doing, so that when it comes time to choose which option is suitable for our design, we know which one to pick. So this will be demonstrated all on this a different file. What we see here is we have a suspended slab. So the this residential slab is supported on columns under. And this particular floor, we have walls spanning between those columns above. So these walls are acting as deep beams, and they will be holding our slab up. So basically, they will be lifting the slab up at mid-span. So the grey columns are below, hatched is walls above, and magenta is walls below. So the simplest option is switching off import reactions from above. So let's say if we haven't run the file in RCB, this will be the only option. So exporting without reactions. And all that does is that it simply exports out the floor. So really, if a floor is a non-transfer floor, we can just have this off for that particular floor. We can just send out the floor itself because the reactions will just go straight down to the vertical elements below, so not needed. But if we're exporting a transfer floor, obviously we would want the reactions for that particular case. So for this transfer floor case, not a suitable option. The next option that we have is reactions via floor area. So the video on the reactions talks in more detail exactly what is meant by static, what is meant by floor area, but I'll just mention it again. What we mean by floor area is that the program automatically calculates the tributary area of the vertical elements and then applies a load to it. So we see when we have export reactions via area, we basically have a uniformly distributed load along the length of the wall. So basically there's going to be no variation in the loading, just a common downwards load. Now for this particular case, is it an accurate representation of what will happen in reality? Probably not. We'll have a look, we'll see later why. But basically this is what we would see in this case if we had export reactions via area and include reactions from above. Next we go to exporting reactions via static analysis. So static analysis means that the structure's frame is taken into consideration when calculating the distribution of the forces. So in this case we have export reactions via static, and we've switched off variable distribution of reactions, meaning that rather than point loads at 1 meter centers being exported, those reactions are averaged along the length of the wall, and then a single uniformly distributed line load is applied along the length of that wall. So again, straight away we see we have net positive downwards loading along the length of these walls, which again might not be representative of the reality that is occurring in these deep beams. So basically this hanging effect, this slab being held up by the wall above, is not really considered in this case either. So the next option we have is exporting reactions by static analysis, but switching on variable distribution of wall reactions. So what we see here is we have the same net total force in basically all of our columns and walls. However, now we're actually considering the true distribution of those reactions in the wall. So looking at this individual wall, we see we have very high reactions positive downwards around the supports, so very high at the column location, still positive downward as we move further away. But as we move to the midspan of the slab, we see these reactions become negative. So we start seeing some negative hanging reaction. So that hanging effect of the deep beam supporting our slab, that is now being considered. So for this particular case, reinforced concrete wall cast in situ, wall acting as a deep beam, this is probably the most realistic distribution of reactions that for this case. So if we were exporting, we really should be using this variable distribution of wall reactions with static analysis for this case. Again, it's just for this case. Other buildings might have basically floor area might be more representative. For example, if it was to be unreinforced blockwork or brickwork. But for this particular case, reactions by static analysis is suitable. And then we have another final option. We have export reactions by both static and area. So what this simply does is it will create two separate files. So it will create the basically the area reaction file as we saw from the previous slide, and then a separate file with static that will have reactions as shown in the last slide that we saw. So those are the reaction settings which are just done here. Next we have the long-term deflection settings. So that is basically we select the program that we set the settings for, in this case SLB, and we hit long-term deflections. So again, we also have the option of changing the settings for all levels or per level. and then we put in our long-term deflection settings as we would in SLB. So this is exactly the same inputs as the SLB software, and all of the various parameters are discussed in detail in the SLB settings video, the SLB long-term deflections video. So straight away we have the option of also doing long-term deflections to Eurocode and the recommended simplified method. And in this case, we've chosen to let the program calculate the creep and shrinkage values for us to AS3600 2009 per slab zone. So again, this is just the screenshot for the 2009 version. This will look a little bit different when the new AS3600 is released, so the 2018 version most likely. So going back to RCB, having reviewed the deflection settings, we'll keep the static analysis reactions to export with variable distribution of reactions. Long-term deflections settings have been set, and we will choose to export and run one of the typical basement floors, the transfer level 1 slab, and one of the typical upper floors. So they will be basically exported to where this SLB directory is set, and then once we hit execute, the program will launch SLB silently in the background, perform its analysis. Then we will view the results as calculated in SLB, so the long-term iCracked results from SLB in the RCB program. So with the batch export and run complete, we hit exit, and then we go to one of the levels where we had performed the batch export and analysis, and under the results tab we see that the SLB PTD results section is active. So we didn't export area reaction, so only static is available. So let's say if we hit deflections SLB KCS, we see that the load combinations for SLB become active. So the screen goes red, indicating to us that we are looking at an SLB file in the RCB software. So we're not looking at RCB results. So if we go now to maybe 50% total 50% KCS total deflections, we can start having a look at these values on screen. So clicking above the walls, we see that basically there's 0 deflections on the walls, and then we have some deflections at mid-span as well. So these, all of the SLB combinations, they were all set up and input when we started making our RCB model. So if we remember back to the inputting of the load cases and load combinations video, that was all done under input and under load factors, for example. So we see we have the SLB load combinations that was set up in the RCB model. So they were set up specifically for this reason, so that when we run the batch export and analysis, the program knows basically knows what its load combinations are. So that was the level 5 slab. If we hit exit SLB, we can then go down and have a look at the level 1 transfer. So results, deflections, SLB, KCS, and then look at the 50% total. So these deflections are looking a little bit too high for 50% steel. And of course, because we'd switched on the recommended simplified method and the Eurocode method, we could also view these SLB calculated long-term deflections in the RCB program. Then if we wanted to continue our detailed design on this slab, so designing and detailing the reinforcement, we just navigate to where we exported the individual files and continue working on this particular floor in SLB. So in summary, what we saw in this video was basically the batch export analysis, why we run it. The main reason being is that basically RCB it doesn't do an iCracked section analysis, so we have to send it to SLB and PTD to get accurate iCracked long-term deflections. So the reason why batch export is run from RCB, so launching the SLB PTD program silently in the background, is so that during the preliminary design stage, when we're determining our slab thicknesses, we don't have to leave the RCB software at all. So we could see for these two separate floors, we could very quickly determine if our slab thicknesses were suitable or not without having to open another program.